In this work, we present FalconFS, a distributed file system designed for the data input workload of large-scale deep learning pipelines. This work was completed during my internship at Huawei Technologies. Let's take a training pipeline for an autonomous driving system as an example. Data are collected as numerous small files in the ingestion stage, then labeled, consumed for training, and archived in the cloud. The training stage has two distinguished I/O patterns. First, each training epoch consumes numerous small files. In Huawei's deployed instance, a dataset consists of 300 billion of files grouped in 1 billion directories. The average file size is around 300 kilobytes, which is relatively a small size. Second, file access in the training stage exhibits poor locality. In each epoch of model training, the training tasks iterate through each file in random order exactly once. This pattern incurs significant challenges to the underlying fine distributed file system. Specifically, the small file size makes metadata overhead significant. For each file read, the client needs to perform path resolution, looking up each directory along the path one by one to check the existence and permission, and indexing their successors. Given that distributed file system stores metadata on remote metadata server, each lookup can be a remote request, which is expensive. Given a 2.4 terabytes per second demand for a cluster of 1,000 GPUs, the corresponding file read is 8 million per second, and the induced lookup request number can be multiple times larger. In this case, the metadata performance of the distributed file system easily becomes a bottleneck of the training task. Traditional distributed file systems absorbs lookup requests with client-side metadata caching embedded in the Linux virtual file system. The client tries to serve lookups from the cache and avoid a remote request on each cache hit. This approach, however, relies on the locality of the application's access to be efficient. That is, that the application should access files in a small number of directories. Unfortunately, the deep learning training task is a typical workload with poor locality, accessing files in random order. It introduces an inherent trade-off for cache configuration. One either allocates a huge amount of memory on the clients to cache the entire directory tree for high performance, which can be as large as several terabytes per client node, or one can cache a subset of the directory tree, which while suffering cache misses that is proportional to the ratio of not cached directories. This dilemma indicates the inefficiency of client caching in DL training workloads. When we perform an experiment to illustrate this trade-off. We deploy a CephFS instance and perform random read on 10 million 64 kilobyte files in 1 million directories. We change the CephFS configuration to adjust the size of the client-side metadata cache with regard to the total size for caching all the directories. As we can see from the read line, as the cache size increases, the throughput increases significantly, indicating that the file system performance is sensitive to the cache size. The bar in the figure expands the reason. As the cache size increases, the number of remote lookup requests reduces significantly, reducing the metadata overhead in the system. It indicates that the metadata performance is a bottleneck for random file accesses. In this paper, we propose a stateless client architecture in place of the traditional client caching approach, which offloads path resolution to the server side. In contrast to client-side path resolution, where clients fetch and resolve metadata, in server-side path resolution, clients send the full path to the server side and perform resolution there, having identical consistency level. Here, we discuss 3 features that makes server-side path resolution more advantageous in this setting. First, the number of servers is typically far fewer than clients. In a cluster, there are typically thousands of client nodes for training tasks. It indicates that it is highly duplicated to cache the metadata on the clients. In contrast, there are typically fewer than 64 server nodes to serve the entire cluster, so we can use a much smaller total cache size to serve the requests. Second, the kernel objects in VFS contains many kernel structures that is not needed for doing path resolution, and the total size can be 800 bytes. However, on the server side, we can use custom metadata objects, which can be as small as 100 bytes on average. Third, on the client side, the DFS client collocate with training tasks, and the training tasks can use high memory spaces, and the introduces the contention is a performance killer. And on the server side, the cache can stand alone and have redundant memory resources. Therefore, memory efficiency is much higher on the server side. However, there are several challenges in building a stateless-client distributed file system. First, for scaling out metadata, it is typical to distribute file inodes over servers. Since the client no longer resolves the path, it is a challenge for the client to know which server owns the target file inodes and send the request to. Second, to scale out path resolution, it is important to enable every server to perform path resolution independently, and thus requiring the maintenance of a copy of the directory tree on every server. It, however, introduces the challenge to efficiently maintaining the namespace replication. Third, given that traditional client-side path resolution is hard-coded in the VFS virtual file system, it is a challenge to preserve the compatibility while offloading the path resolution logic out of the virtual file system without recompiling the kernel, which is unfavorable in production environment. In this paper, we propose FalconFS, a distributed file system designed for deep learning training pipeline. It consists of 4 components. The client takes application requests and forwards them to the end node. The coordinator manages complicated operations such as rename, and the file stores keep file data. In FalconFS, inodes and the entries are stored as key value objects. The entries are replicated while the inode are partitioned. FalconFS adopts 3 designs to address the above-mentioned challenges, which we then explain in detail. First, FalconFS adopts hybrid metadata indexing to locate file inodes. In the common case, FalconFS locates file inodes with file name hashing. For example, to open a file with a path /data1/1.jpg, the client compute hash 1.jpg and find the file is on node 0. This approach can produce an even distribution of files in the common case, since we observe that in deep learning workloads, the file system typically stores the data set, where the number of files in the directory is often far larger than the number of servers. Given that files in the same directory have unique file name hashing can produce independent uniform distribution of files in the same directory and thereby the entire directory tree. However, file name hashing also gathers files with the same name to the same node, which can be a problem. To handle this problem, we introduce selective redirection. Specifically, FalconFS maintains an exception table on every end node, and the clients get an updated of them on every response. Once the coordinator observes a loading imbalance, it can add an entry to the table requiring files of specified name to be partitioned by hashing parent ID and name. Then the client accesses such a file. It then sends a request to a random selected node, and the node resolves the path locally and forwards the request to the correct node, finalizing the request. FalconFS can also specify files with a specified name to be placed on the specified node to mitigate load imbalance induced by hash variance. When a client accesses such a file, it then sends the request to the node that is specified by the exception table. Then I will introduce how FalconFS manages server-side namespace replicas. Specifically, it adopts lazy synchronization instead of an eager one. To create a directory, it just send the request to the corresponding node and to create it over there. When we need to look up a directory on another node, it just fetches the node. It fetches the inode from the corresponding node. And when the directory needs to be updated, FalconFS just invalidates all the replicas on the other node and update the inode of the true copy, and then the other nodes can fetch it from it. This approach is very similar to the cache coherence protocol. And now I introduce how to implement VFS compatibility. FalconFS supports VFS compatibility via VFS shortcutting. Specifically, it distinguishes lookup requests to intermediate path components from those to the last component by leveraging a flag, namely lookup parent, which already exists in the kernel. If a lookup request goes to an intermediate inode, the client module returns a fake permission that has 0777 to just pass the check in the VFS. And if a request is looking up a final component, the client module sends a request to the end node to do the real check and give the result to the client. Now I will introduce the environment setup. We perform environment on 16 server nodes and compare with several state SOTA systems. The metadata throughput, FalconFS has a good basic metadata performance, and its metadata performance is scalable. And we also conduct data throughput environment and find that for file accesses of small I/O, the advantages in the metadata performance results in much higher data throughput, and it is very favorable for deep learning workloads. We also conduct an impairment for the load balance in real workloads. It indicates that for most workloads, we do not need exception entries, and for non-favorable workloads, a few entries is sufficient to acquire a balanced distribution. For the workloads with constrained memory, we can achieve a very stable high performance when the memory resources are constrained. And end-to-end evaluation shows that FalconFS can achieve higher GPU utilization since the I/O bottleneck is solved. And here is the conclusion. In this paper, we solve the problem that traditional path resolution architecture is a bottleneck for random file access. And we introduce 3 key technologies of FalconFS. The result shows that FalconFS achieves stably high performance in numerous file random access workloads. And in deployed environment, it can reduce the storage cost by higher than 50%. Thank you very much, and I'm happy to answer questions.